In this video, we are going to practice using molar mass, Avogadro's number, and formula ratios as conversion factors in dimensional analysis. There are three units we commonly work with in chemistry: mass, measured in grams, amount of substance measured in moles, and particle counts, which may include atoms, molecules, or formula units. To convert between grams and moles, we use molar mass as a conversion factor. To convert between moles and particles, we use Avogadro's number as our conversion factor. Molar mass and Avogadro's number both describe relationships between moles and another unit. The mole acts as the central unit that connects these different measurements. Let's work through an example problem. What is the mass in grams of 7.03 times 10 to the 21st formula units of NaCl? When reading the question, we should look for keywords that tell us which conversion factors we need. We are being asked to find mass in grams, so we know that we need the molar mass. We are starting with formula units, so we know we need Avogadro's number. Because we need to use both relationships, we will need to use two conversion factors. First, recall that 1 mole of NaCl is equal to 6.022 times 10 to the 23rd formula units of NaCl. This is the relationship provided by Avogadro's number. Next, we need the molar mass of NaCl. From the periodic table, 1 mole of NaCl has a molar mass of 58.44 grams. Next, we can begin by setting up our dimensional analysis. Start with the given value, 7.03 times 10 to the 21st formula units of NaCl. It can be helpful to write this over 1 so that you have a fraction. Next, set up your first conversion factor. Copy the unit and the substance label from the numerator into the denominator of the conversion factor so that it will cancel. Because formula units are both related to moles through Avogadro's number, we place the 6.022 times 10 to the 23rd formula units of NaCl in the denominator and the 1 mole in the numerator. We still need to convert from moles into grams. Set up our second conversion factor by copying the unit from the previous step into the denominator. The molar mass goes on the opposite side, 58.44 grams of NaCl divided by 1 mole of NaCl. Now our units will cancel, leaving us with grams of NaCl. Enter this into your calculator, and you should get that 7.03 times 10 to the 21st formula units of NaCl is 0.6822 grams. We need 3 significant figures in our final answer, which is 0.682 grams of NaCl. If you did not get this answer, double check your calculator entry. In particular, make sure that your exponent for Avogadro's number is correctly placed in the denominator. You may need parentheses around the denominator to make sure that your calculator follows the correct order of operations. How many formula units are in 1.34 moles of K3PO4? The phrase formula unit tells us immediately that we need Avogadro's number. Recall, 1 mole of K3PO4 is equal to 6.022 times 10 to the 23rd formula units of K3PO4. Begin with the given value, 1.34 moles of K3PO4. Set up a conversion factor so that moles will cancel. The moles of K3PO4 go in the denominator. 1 mole of K3PO4. The number of formula units will go in the numerator. 6.022 times 10 to the 23rd formula units of K3PO4. After calculating, we find that 1.34 moles of K3PO4 is equal to 8.069 times 10 to the 23rd formula units of K3PO4. We need three significant figures, so the final answer is 8.07 times 10 to the 23rd formula units of K3PO4. Remember that when you round for significant figures, you need to include the power of 10 in your final answer. The chemical formula of a compound can be used as a conversion factor. We call this relationship a formula ratio. A formula ratio helps us relate a whole object to the individual parts that make it up. For example, one spider has 8 legs. One chair has 4 legs. One water molecule contains 2 hydrogen atoms and 1 oxygen atom. Because we often work with moles instead of individual molecules, we can extend this relationship to the mole scale. 1 mole of water contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms. The subscripts in a chemical formula tell us this formula ratio. Calculate the moles of oxygen in 1.7 moles of calcium carbonate, CaCO3. Look at the chemical formulas of what we are given and what we are trying to find. We are given calcium carbonate, and we are looking for oxygen. Since the chemical formulas do not match, we need to use a formula ratio. The subscripts after the oxygen tells us the ratio. 1 mole of CaCO3 is equal to 3 moles of O. Now we can set up dimensional analysis. Start with 1.7 moles of calcium carbonate. Copy the unit and the chemical formula into the denominator of the conversion factor so that it cancels. Place 3 moles of O in the numerator. The calculation is 1.7 times 3 is equal to 5.1. Therefore, 1.7 moles of calcium carbonate contains 5.1 moles of oxygen. Now let's try a problem that requires all three conversion factors. How many nitrogen atoms are in 56.04 grams of dinitrogen tetrahydride, N2H4? First, identify the conversion factors needed. The question asks for nitrogen atoms. The word atoms tells us that we need Avogadro's number. The mass of N2H4 is given in grams, so we need molar mass. Finally, the compound and the element we are trying to find are different, so we need a formula ratio. Let's start by calculating the molar mass of N2H4. N2H4 has 2 nitrogen atoms and 4 hydrogen atoms. The molar mass of N2H4 is 32.045 grams, and that's equal to 1 mole of N2H4. Now let's think about the formula ratio. 1 mole of N2H4 has 2 moles of nitrogen. The subscript on the nitrogen tells us this ratio. Lastly, let's think about Avogadro's number. 1 mole of nitrogen atoms is equal to 6.022 times 10 to the 23rd atoms of nitrogen. Let's begin with our given value, 56.04 grams of N2H4. First, convert grams to moles using the molar mass. Next, convert from moles of N2H4 into moles of nitrogen using the formula ratio. Lastly, use Avogadro's number to get into atoms of nitrogen. After completing the calculation, we find that 56.04 grams of N2H4 is equal to 2.106 times 10 to the 24th atoms of nitrogen. This type of problem combines all of the major conversion tools that we have learned. Molar mass connects grams and moles. Formula ratio connects compounds and their parts. Avogadro's number connects moles and particles. These three relationships allow us to move between the laboratory scale measurements that we can make and the microscopic particles that we cannot directly count.